I'm very pleased to introduce our speaker today, Professor William J. Ullman from the University of Delaware. And he has a long and distinguished association with me and also with Josie in the sense that actually I first met Bill when he was an undergraduate at Yale University and I was a graduate student, and we were diving partners for several years out in Long Island Sound, and he pretty much ensured that I didn't kill myself. He was a dive master and highly trained in underwater activities. And he then stayed at Yale after he graduated and, believe it or not, worked for Josie, who was a postdoc at Yale at that time. And then he went on and did master's work at the University of Michigan, and then came to the University of Chicago, where I was at that time, and became my first PhD student there. And so we have kind of this long history together, and did a lot of field work together, particularly when he was a graduate student at Chicago. He worked at that time on the sedimentary geochemistry of iodine and bromine, and did basically the earliest detailed process-oriented research on iodine and bromine chemistry in sediments. And that's become more topical again as a result of the Fukushima incident, in which there was tremendous amounts of radioactive iodine released to the environment. So people have this renewed interest in that after multiple decades of quiescence, I suppose. He went on to Australia and worked on evaporite processes in Australia near the Gulf of Carpentaria, and then came back to the United States and worked at Argonne National Laboratory on the thermodynamics of transuranic elements in solution, and he's gone on since to work on a number of different topics, and most recently, in the last 15 years or so, he's emphasized groundwater inputs into the coastal ocean, and as you'll see today, the monitoring of high-frequency types of changes in coastal water chemistry. He's also been visiting professor in France, and from time to time we pass over the Atlantic, I guess, going back and forth to France, because both of us enjoy being in France quite a bit. Yeah, he speaks French, I don't. So that's one major difference. I've been trying for years, but he's been successful, and I'm not. So I'm very pleased, Bill, to welcome you here, and we look very much forward to it.
Thank you, Bob. Thank you, Josie. Anyone has any problems hearing me, let me know, and I'll try doing whatever is necessary to make that easier for you to do. I'm very pleased to be back here again. The last time I was here, I talked about the groundwater discharge to the ocean. I'm going to talk about a different topic today. And Bob did make me promise when I arrived here that I would show no pictures of him or Josie in bathing suits as part of my talk. I have a collection in case anybody ever needs them. Please let me know. I have a lot of those things from days long gone. So I'm going to talk today about continuous or really semi-continuous automated water quality monitoring, and I'm going to emphasize watersheds and estuaries because I work both on the freshwater sides of watersheds as well as what goes on in estuaries. And I'm also going to emphasize the point of view that what I do is both useful for management, which funds my research, as well as for research. So I'm going to go back and forth talking about kind of management issues and some scientific issues, and try to give you some examples of work that we're doing at present. Before I start, I always never leave time at the end to give credit to all the people I work with. I have a very good group of collaborators at the University of Delaware and in Delaware. Scott Andrus, who is a surface water hydrologist, I met the second month I was in Delaware, and we've had 25 years of funding together studying watersheds, chemistry of watersheds, and hydrology of watersheds, and how that hydrology affects small estuaries in Delaware. So we've been working for a long time. Ko-Chin Wong is a physical oceanographer, graduate of this institution, who works with me now on time series analysis, but he's been my what I would say my physical oceanography ground truth person for, say, 27 years I've been at Delaware, and we're still actively working together. Anthony Alftenkamp is a researcher at the Stroud Water Research Center who's been pushing me in the last few years to start looking at carbon cycling and looking at particles, not just dissolved substances, and I'm learning a lot from working with him. The rest of these people, Brian Zwankowski was a postdoc with me, he's now at the University of Maine, is a remote sensor by training and does a lot of time series analysis and is starting to basically teach me how to use the kind of continuous data we're collecting because he's the guy who knows how to look at the time series. Joanna Voinova is a new postdoc working with me who is interested in nutrient cycling in estuaries, but also has a very physical bent. How does physics of estuaries, how does the water flow control be observed in chemistry on various time scales? Sarah Fisher is a new graduate student who's working with me. These two guys have been really important to me. Hans Bedlarz is the Director of Public Works for the Kent County, which is the central county in Delaware, and has been funding my work since 2007, and has been very generous to provide funds for equipment that would otherwise be hard to raise funds for. And Hassan Mirsajadi is at the Department of Natural Resources and Environmental Control, and has been supporting my work since 1999, looking at nutrient cycling in estuaries. The rest of these people are people who have come through the lab, and some of the work I'm talking about is theirs, and I'm just I had the luck to be the person who gets to present it. Also want to thank, so this is kind of to thank Hans. Hans is the Director of Board of Public Works for Kent County and runs on the side something he refers to as the Kent County Science Foundation. Very, very generous with funding and very, very generous with in-kind assistance. And the work that I talk about in the murder kill was all entirely funded by the wastewater treatment plant people in the Board of Public Works. And he allowed me not just to do the stuff that they needed for management, but to ask some scientific questions with the funding. So he's very important. DENREC has supported my work. The Delaware Geological Survey, which is part of the University of Delaware, has supported the work. USGS has provided in-kind assistance at various times. Sea Grant has supported it. The Center for the Inland Bays, which is a national estuary program in Delaware, has supported some of this work. And recently, DuPont, through their Clear Into the Future program, has been supporting students to work on a combination of monitoring and scientific management of estuaries. So I've got sources from a lot of different places. What I'm talking about today couldn't have been done without that money. So what I'm going to talk about is the need for continuous sampling, or what really is semi-continuous sampling. I'm going to talk a little bit about instrumentation, and then I'm going to give you kind of a vignette of different results we've had from different studies we've done. Pond studies, river studies I'll talk about. And then I'll talk about some marsh work we did, which actually is semi-continuous, but was all done with traditional analytical methods, meaning we collected samples and analyzed them. But this work is what actually justified us going into more automated kind of sampling when I talk about estuary studies. So I'll talk a little bit about this, and then I'll come back at the end and talk about where I think the future is going for these kinds of this kind of research. So management needs, the biggest driver of the research that I do, what's providing the funding, is there's been a change in how we manage nutrient loads into freshwater and coastal ecosystems, and those are changing regulations that apply to wastewater treatment plants and to agriculture, to other land uses within a watershed. And in order to justify all of this, the managers need to have accurate, justifiable estimates of actual nutrient loads. It's no longer enough to say, we think it's this way and this is the problem. You need to have the data, because it's the data that convinces people to put the money into the projects that are needed to reduce nutrient loads where they're needed, and make sure that that money is spent effectively reducing the nutrient that needs to be reduced in that particular ecosystem. The other thing that's coming in right now that's getting more important is distinguishing between what is kind of the average everyday behavior of estuaries and what happens after big episodic events, Hurricane Sandy kind of events, any hurricane you can think about. What happens during those hurricanes? And what I'll tell you from my experience is it's getting harder and harder to get graduate students to sit out and take water samples in the middle of hurricanes. We used to do that all the time, right? And now it's just harder to get people to do that. And so The only way you can really study the storm events and the effects of storm events is to have some kind of an automated system out there that involves, to a lesser extent, graduate student effort than just sitting out there during the storm. Research needs, the big thing that we've been working on is really how do estuaries change when there's an event, or how does a pond change when there is an event. Event can be just wind. In the case of estuaries, winds have a big effect. But wind and rain rain alone has an effect. Wind and rain have different effects. And some of the things that we're looking at in research questions are, how does estuarine circulation drive the chemistry, drive the loads, drive the processes in small estuaries? So this has been really the major driver. Recently, because of various estimates of what climate change is going to bring in terms of weather patterns to the east coast of the United States, there's been a lot of concern about what's going to happen. How are estuaries going to behave? How are nutrient loads going to change once we have more frequent or larger storms occurring in the mid-Atlantic, which are both possible scenarios in the next 50 to 100 years. So these are the kinds of things that we're kind of our overarching themes that are driving our research. So let me tell you a little bit about why I got interested in this. I've lived for a long time with what I call physical oceanographer envy. And that is, physical oceanographers have all of these different sensors that they can put in the water, and they almost instantaneously get results. And they can get results that are, fixed in position, what's happening and changing in that position. They can look down from space and get XY plane variation. And if they look multiple times at the same frame, they can get XY and T. And they can also now, with acoustic Doppler and kinds of things like that, get essentially a whole field of X, Y, Z, and T data with just putting an instrument in the water. And I'm left with the ability to go out there and grab a sample about every 2 weeks and spend 2 weeks analyzing that sample. And then they come to me and say, okay, well, what's controlling the nutrient loads in your system? This is actually salinity, which is relatively easy to measure with modern equipment. And this is actually degraded. I've only plotted every hour's worth of data. We actually collect this data every 6 minutes. So it was impossible. It takes too long to plot. So I just eliminated the data. And this is the typical kinds of sampling that we do. And then someone says, okay, what are the processes controlling nutrient loads? How can you answer that question when you have such a sparse data set on nutrient concentrations? You can improve this a little bit going from a 2-week interval to, say, a 5-day interval, but you don't gain a whole lot from a 5-day interval. You can go to a 1-day interval, and I would guess if I looked at this data set, I would just attribute most of that to variability and not see anything that I could identify as a trend. It's only when you start collecting data at the same kind of resolution that you can collect salinity that you can start identifying processes that are controlling nutrient concentrations at the same rate as controlling the salinity, and from that get some idea of what is affecting load. So my reason for getting into this business was I want to be able to collect the same kinds of data and have the same kind of certainty about nutrient loads that a physical oceanographer has about flow. So get over this problem of physical oceanographer envy. So what are the instrumentation that's available to us? The simplest thing is we can go out and sit out there and sample every hour, filter, store the sample, analyze the sample. You do this for too many hours and you're committed to an awful lot of analytical work afterwards. So it takes a long time to do, this is easy sampling, but to get to the actual data is very complicated. So this is our traditional way of doing this. I did this once at Oyster Landing in South Carolina when I was a graduate student working with Bob. The experiment didn't work. We didn't see any variation in the time period we were looking, but this is still not a bad way to do it, and I'll show you some data from this kind of thing. We've learned a lot from this kind of method, but it is very, very time-consuming, effort-consuming, and it's essentially too expensive to do very often anywhere. The second method is to basically use pump systems and use traditional analytical methods. And this is Imagine, for example, that you have an autoanalyzer, the typical autoanalyzer you have in a lab, and you just pump up to your autoanalyzer a sample and run it into your autoanalyzer, and you can get continuous data like that. The problem with traditional autoanalyzers is, first of all, they need a lot of power to run. They need people to maintain them. They need to have reagents replenished on a regular basis. This is not a bad way to go, but it's not a way of getting long-term continuous data because you're going to have people involved in every step of this thing. So you basically have to commit a person to operating this kind of thing to get data from one point. You can improve this a little bit by going to pump systems with somewhat less traditional methods that use less in the way of reagents, for example. But some of those methods work better than others. We've experimented with a little bit of this kind of technique, and I'll show you some data from this. The big jump is getting into in situ sensors, where you can just put them in the water and power the sensor. So you run 2 wires down and have the sensor report back to you running 2 wires up. So 4 wires in the sensor, and you're in really good nick. And this is the direction that we have been going, and not just us, but this is the way the industry is going, of having more in situ sensors available for different things. And there are now commercial sensors available, and I'll talk about those commercial sensors. And anybody who wants more information, I brought the brochures from the suppliers if you want to have a look at the kinds of instruments that are available. There's some literature right down here. And then there's some hybrid systems where you have some in situ and some other kinds of systems. And I think this is important because we don't have sensors for everything. So things that are in situ sensors plus perhaps traditional sampling, or some in situ sensors plus something that's pumped up to a pump system are probably going to be useful for some kinds of studies. We haven't tried this a whole lot, but I know people who are experimenting in this kind of realm. So the sensors that are available, well, I guess I would say these are the physical oceanography things. Salinity, stage height, depth, temperature. They're really good nephelometers, turbidity sensors, which operate on pretty much low voltage, good resolution. I would call this sensor kind of revolutionary, the ability to have a solid state sensor that does nitrate, because one of the things we're interested in is nitrate concentration. There are now 2 companies making these. Satlantic is the one I've been using. I have a Suna, and SCAN is an Austrian company that's making similar sensors. The SCANs are really designed primarily for wastewater industry, so they are high concentrations, and they don't have the same level of anti-fouling that a typical marine sensor would need. The Satlantic Suna sensor was designed particularly for high fouling environments, so it's a little bit better designed for many of my applications. Deployment requirements, there's some limits in terms of pressure. A lot of these are in pressure cases, but they're not high pressure cases, so you're limited to a few tens of meters for deployment for most of these units. Biggest problem that we are having in one of our sites is that we have such turbid waters, and we have an in situ pumped sensor. It pumps the mud in, but it doesn't pump the mud out, and that's not really good for sensors. Fouling is a problem. We've had 2 or 3 episodes where we've come back and our sensor looks like an oyster reef instead of a chemical sensor. And one of the nice things about the instrument that we're using in salt water is that it's pretty much made out of copper, everything that's exposed. And that helps a whole lot, but not entirely. There are things that will stick to the copper on occasion. And so there are other sensors, these pumped and in situ flow through analysis. You can get there is an off-the-shelf phosphate analyzer, which is basically an autoanalyzer in a can. And it basically just plug it in, it sucks in samples, it has reagents, it does the same reagent that you would do, the molybdenum blue reagent method, and it reports the results back. There's a similar one for ammonium that is coming out this summer. And the problem with these, at least in our site, is because of the small tubing we use in our autoanalyzer, so we can use very small volumes. We plug up our tubing all the time, in spite of various filters along the way. There's enough material in our system that these are not been very successful. And I probably won't show you any of the data from the instruments we have. So. We have 4 projects that we've done. Some of these are completely done, and some of these are still in progress, but I'm going to talk about work that we do in ponds, and that's because I start with this idea that I learned from working with Scott Andrus, that you really need to understand watersheds and what's happening in watersheds in order to make reasonable prediction about what responses are going to be in the estuary. And so we work in kind of all watersheds. We work everywhere from the freshwater end all the way to the seawater end of our estuary systems. I'll talk about rivers. I'll talk about this study a little bit. I'll talk about rivers. Right now we have a site we just started in October, which is in the Chesapeake Bay watershed, and I'll talk about the work we're doing there in the Nanticoke. This was a study that was all done with manual sampling, and I'll talk about that because we learned a whole lot about how exchange of nutrients happens between marshes and estuaries. And we have some estuaries in our system that are very much marsh dominated, where the waterways represent 10% of the estuary, 90% is marsh. And so exchange of nutrients between marshes and the estuary is of major importance in that particular estuary. And then I'll talk about this newest sensor. This is the LOGO sensor that we're using, which is designed for marine applications, semi-continuous instrument with many sensors on it, and you can add sensors to it. We actually have 5 different things plugged into it right now, but you can unplug one and plug in another if you want. So there are other sensors that are coming online that we may replace the ones we have. And this is in a place called Bowers, Delaware, just south of Dover, Delaware, in the unfortunately named Murder Kill estuary. Kill just means creek. Murder probably comes about from a misspelling of an older name, but it's we work a lot in the murder kill and has nothing to do with murder or kill. The reason we work in the murder kill is this is where the Kent County wastewater treatment plant discharges to this estuary. So this is how we get funding. Is the funding for that work is all related to the operation of that wastewater treatment plant. So the pond studies were largely focused on determining actual loads and comparing them with what the loads which were proposed in regulation for regulating the water quality of Delaware's inland bays. So I'll talk about that. Millsboro Pond is where we set this instrument up, and I'll introduce you to the instrument in just a second. It's the largest watershed draining into Delaware's inland bays, which is Indian River Bay, Rehoboth Bay, and Little Assamoman Bay. And down in the very southern part of Delaware, you almost can dribble off into Maryland down there. And so it was a good place to kind of look at representative discharges from the watershed to the estuary, because it reflects a large fraction of the area of the watershed. The other thing is Delaware has no lakes. How many people knew that? One person, good. Delaware has no lakes. We have lots of man-made ponds, and so this is actually a very representative of what man-made ponds are doing all over Delaware, of which we have, depending on what you call the limit, there are 18 of them, man-made ponds in Delaware. So we do have something that looks like lakes, but they're all fakes. The scientific questions that we were asking as part of this study was, to what extent do ponds moderate the loads? Or essentially, can we treat the pond as being a kind of a wastewater processing system? Is it actually reducing the loads downstream? And the other thing that got us interesting is from not very continuous data. There seemed to be a thing in Millsboro Pond where it operated in one mode where it was more phosphorus high, nitrogen low, or nitrogen high, phosphorus low, and it would switch back and forth. It didn't seem from the data that was collected in the past, which was monthly data, that it was following any particular season, but we were interested in getting some information about how these ponds switch seasonally or switch back and forth between these different modes. And I'll give one example about this mode shifting as we talk about this. So this is the land use. Mostly it's ag, a lot of wetlands and forested areas. Water makes up a small amount, 14% of this is urban. Urban means suburban developments in most cases in this, anything that's built up. Millsboro Pond is located here. This is just a larger, showing a larger watershed of the whole inland bays. This is showing where the site is on both of these maps. And this is where we are in southern Delaware. This is the instrument that we used at this site, which is an Australian instrument. It was designed for doing, it's a freshwater instrument. It uses ion selective electrodes for doing nitrate and ammonium, and those don't work in saltwater systems. It has an onboard single channel phosphorus analysis system, which is based on the molybdenum blue system. It does measure temperature, conductivity, dissolved oxygen, and pH. It basically is more or less traditional methods. The ion selective electrodes, you might say, is a little bit non-traditional for the oceanographers, but it's commonly used in freshwater environments. It has a temperature control module, and it's mounted in an insulated box. It's underneath that, there's a computer which both controls the instrument and controls the 36 valves and 3 pumps that are inside of this, which basically circulate the sample and all the reagents to the right sensors at the right time when it's working. And then this is the reagent storage pool. Actually, these are all reagents. This is a cleaning solution. It cleans itself every 24 hours. It just runs boric acid through every tube, because if you didn't do that, it would get fouled. This is actually the waste container. There are 2 waste streams out of this. If all the waste is just the water, it goes right back out into the environment. If they add any chemicals, it goes into a waste container. That has to be replaced every about 3 weeks on a normal operation. What else can I tell you about this instrument? It has some very primitive computer control. This is a 7-year-old instrument. We're getting to the point where all our modern computers can't communicate with us. So if anybody has a laptop XP computer, I want it. They're getting hard to find.
How many would you like?
We can talk about it. But this is getting to be a little bit of a problem. We have the original computer that came with this is giving us problems, and finding replacements is tough. So, and these are the things that it can measure. So this is just showing the site where we were on Millsboro Pond. We actually had the state come in and build a platform for us. This is the little shed that we put it in. We learned a lot about having a very small shed. We thought it would be really nice. It won't be very visible. But I spent an enormous amount of time on my hands and knees crawling around the edges of this, trying to make it work. And I'll show you that now we have a new system. We're using this instrument in another place. We're doing a lot better. And it was really fun because I got to use really big equipment to install this. I had to get a crane in there. The problem with this is the electrical wires. We picked this whole site thinking that we were going to move the instrument there and then build the shed around it. And that didn't work out. And then we discovered once we had built the shed that we had electric wires right over it. And so getting the instrument in was a little bit of a challenge. And we did get that in eventually. I was a little bit worried when the crane cable got within about 2 feet of these high tension wires right next to it. But the crane operator just did it. You know, we do this all the time. Much more. So here's the kind of data we get on this. This is the one thing I should say about this is the instrument doesn't work all the time. It shuts down. Keeping it running, particularly when you want it to be running and it's important, is hard. It can run out of a reagent and it'll shut down. A little fluctuation in the electricity will shut down. It's designed to protect itself. So there are little gaps in here. This is just looking at this problem of this mode shifting problem. We picked this. What you see here is discharge measured by the USGS at the site, temperature measured by our instrument, conductivity measured, pH measured by us, and turbidity measured by us using the Aqualab instrument. What we did here is the yellow, blue, and green here separates the rising limb, the peak of the storm, and the re-equilibration back to base flow. And the reason I pulled this one out because this is a good example of this problem we have with peak shifting here. If you look at, this is the same discharge. Rainfall's been added to this, so this is daily rainfall because that's what we had available at the time. Now you can get rainfall every 10 minutes with the appropriate sensors, but we didn't have that available. One of the things I want you to note is that this is nitrogen here. nitrogen, and this is actually nitrate plus ammonia, but it's mostly nitrate. What you see here is that nitrate concentrations go down during the latter part of the discharge. As a result, the nutrient loads, this is the nutrient load before the storm, goes up a little bit when the rising limb goes up because you're increasing the flow. So the load goes up because you're increasing the flow, not because you're changing the concentration. As the peak flow goes by, however, concentration is now dropping, so the loads drop. So when you start a storm, you push out a lot of nitrogen initially, but then the nitrogen loads go down, and a few days later, you're back to somewhat lower, a little bit lower nitrogen loads, but that's than you started out with. But you're basically come back to more or less a steady state. And I'll show you an example of that in a second. Phosphorus behaves completely differently. Phosphorus stays low until the very end of the storm and then goes up, and it stays up. And in fact, in this particular case, it stayed up for weeks after the storm. So this was an example of the kind of mode shifting that we had seen by only seeing, a sample here and a sample there. We didn't know what was happening to drive it. It turns out that when you get to the right season, which in this case was late fall, and you have a storm, the system doesn't come back to its initial steady state, it comes back to a new steady state. And that's what happens in this system. For example, that's the load of phosphorus that we've had before the storm, and during the storm it went up and it stayed up. So we went from a system that was dominated by nitrate, and in one storm flipped it to something that was dominated by phosphorus. I'm not going to talk a whole lot about this, but our typical storm, and this is actually the storm that I just showed you, but our typical storm, you start off, initially you increase the flow, that's flow along here, but the concentrations stay the same. Essentially what you're doing is when the flow of the streams goes up, it's essentially flushing out the volume of the pond. So the concentration doesn't change, but you increase the load because you're increasing the flow. At a certain point, you start seeing the effect of the storm, which is to lower the nitrate concentrations. And then when you have the recession curve, you come back towards this red line, which just represents a constant load line. Okay, you take the load that you were measuring before the storm, and you say, okay, given that load, I want to hold that load constant, but for change discharge, this is what the red line represents. And typically, what we see for storms during the summer is these come all the way back to the original. So we go through a circle on this diagram, but you come pretty close back to the starting point. But when you do this in the fall for nitrogen, you don't get back to the same place. And I think so there's these events that happen, and they just change the steady state. This became the new steady state concentration. Behavior for phosphorus was really distinctly different. We did the same flushing initially, but the effect of the flushing, at the end of the flushing, that's when the concentrations go up. And it just kept going up, and it stayed high. So at this particular season of the year, we don't actually have really good, we see for little storms things that go back and forth, but for at this time of the year, a big storm puts it in a completely different mode. So if you're using your wastewater, you're using the pond as a way of regulating nutrients, you need to know that that pond is, after a storm, is going to behave perhaps differently than at the beginning, and take that into account in terms of your management of the pond plus wastewater system that is now working on your behalf to prevent nutrients getting out to the estuary, into the ocean. Okay. Let me talk about river studies. We started these in 1999, and that's me doing the traditional method of dipping a bottle in. My students obviously were sitting up here taking pictures of me while I was doing that. This was a pretty muddy place. When we were doing this, we did base flow by dipping, and then the big technology at that time was these ISCO samplers, which are essentially a pump with a rosette of 24 bottles. And you can program it to take a sample at fixed intervals and fill a bottle at a time, and then you can collect 24 bottles and analyze 24 bottles to look at storms. We did a lot of storm, and this ISCO lived in this little doghouse that we built, and we looked at 6 tributaries to the inland bays and got at a minimum of 6 storms at each of those tributaries. It took us 2.5 years to get that done. It was pretty complicated. Power failures were an issue. People shooting our power supply, which were solar panels, was an issue. There were a lot of different things here. Some of we had actually built into this system a system where we could turn the machine on by telephone. We had no way of verifying that it actually did that. So after the first couple of months of trying to turn these on automatically, and sometimes it worked, sometimes it isn't, we got in the habit of going out the day before every storm that we wanted to catch, turning them on manually, which meant we wasted the first few bottles in order to get the rest of the bottles. We actually accomplished everything we wanted. It was all manual analysis, so 1 day of data collection could take us 3 to 5 weeks to analyze all the data. And during that time, we weren't out collecting another sample because just imagine the number of bottles. We had 6 sites, 24 bottles that we had to deal with every time we sampled. The other downside of this is that when you use the ISCO, your sample actually sits in the ISCO for a period of time. And even though the ISCO has ice put into it when you're loading it, often when it was warm in the summertime, the ice melts, so it's not really being kept cold. And you allow continued reactions going on between the particles in your system and the fresh water. So we're never absolutely certain whether the dissolved materials we were analyzing were actually dissolved at the time that we collected, or whether they had come off the particles, or vice versa, which meant that we had to report loads by doing both particle sampling and analysis and dissolved sampling and analysis on every sample. So it actually, the use of this required us to do more analytical work, and that's probably not, that wasn't sustainable, I can tell you that, because I had at least one technician throw up her hands and said, I'm going to nursing school, I can't do this anymore. So, the most recent study, and this is just started last October, is in the Nanticoke River watershed. This is the part of Delaware in the southwest that actually drains not to Delaware Bay, but to Chesapeake Bay. And our funding comes through an EPA and a Chesapeake Bay program source for this. This is pretty typical of land use. I should point out that this is land use on a log scale here, so it's really dominated by agriculture. Even though it only looks like it's a little bit higher, that's the log scale problem. And we have a site here near Bridgeville. The town of Bridgeville is right here. If you drive from Washington, Route 404 comes right past our site. And that's a new site, it started in October. We're just collecting some data. I'll show some of the stuff we're doing there. But this is really to constrain, to identify whether management practices that have been put into place in the past have affected loads that they've calculated from the past, and whether continued management is going to make a difference. So this site is located on a kind of marshy area around east of Bridgeville. It's located right here. There's actually more residences than currently show on this map. Here we have the USGS gauging station. And having gotten smarter about sheds, I now have a real lab out there, which is 10 feet by 16 feet. It's an old lab van from a ship, which is insulated, air conditioned, heated. We have running water, but it's sample water. We don't want to drink that, but coming in. So we actually pump from the adjacent stream here underground into our shed, and our aqua lab now sits in that shed and does its analysis there. Management questions here, and this is what's funding the work, is have the nutrient load changed since our previous study. The previous study we actually did in 2002, 2004 using the ISCO samplers. So we collected the original data. They're now coming back and saying, we put all these, in response to that, we insisted that the town of Bridgeville eliminate their direct discharge of wastewater to the Nanticoke, what's upstream of our site, and that they move it to a spray irrigation system, still upstream of our site, but on the other side of the river, And the question is, has that actually changed the loads? So we're not even done with a year yet, so we can't answer that question, but that's what was driving this work. Was basically the management practice they put into place was you, Bridgeville, have to stop discharging directly to the stream. You have to put it in spray irrigation. We're going to grow crops there to remove some of the nutrients from spray irrigation. We put it further away from your discharge is in an area where there's going to be probably 5 years average flow time between where the discharge is and where the nearest tributary to the Nanticoke is. Has it made any difference? You spend a lot of money and force people to do things, you want to show that it's made a difference. And ultimately we have to come back and update what our loads were from what we measured in 2002. We've gotten much more interested in what happens during storms. It didn't hurt to have Hurricane Sandy occur within the first month of having this out. So, and by the way, the water got to within 2 inches of flooding our instrument, even though we're 20 feet above. You know, we're supposed to be 2.5 feet above the maximum recorded high tide ever, or high water level, and Hurricane Sandy was pretty spectacular. Flooded the whole area. If I haven't told you this, Delaware is like a pancake. It's flat, so flooding is easy. So there are a couple of things that we noticed at this site and also at Millsboro Pond, and that is that during the summer particularly, we see patterns that are not completely periodic, but somewhat periodic, that are about 7 to 10 day length. And the only driving force that we know of that is 7 to 10 day are weather patterns. And so we kind of asked this question, are we going to see patterns that are 7 to 10 day patterns in this system as well, driven by weather patterns? So cloudiness versus sunniness, that kind of stuff, temperature changes, things like that. And so this mostly happens in the summer. We only had this instrument in since October, so I'm not going to tell you anything about that because we don't have the data yet. But we do have a question about how do storms affect loads? Do storms lower the loads or raise the loads, or how does it change the relative amounts of phosphorus and nitrogen loads? That is a question that we can address also from this data. So here's data from, well, this is from November until, 3 weeks ago? 4 weeks ago, something like that. And this is typical. Discharge is still measured by the USGS. They do a great job for this. They report it every 6 minutes, so every 10th of an hour. We're doing measurements basically on an hourly basis for conductivity, temperature, pH, dissolved oxygen saturation, and turbidity. A couple of things I want to point out that show kind of stream ecology at work is that when we have a storm, which are all these peaks that you see here, we see a decrease in conductivity associated with that. I'll explain why that happens. We see an increase in turbidity associated with that storm, and we see basically a change in the patterns of dissolved oxygen. There's so much turbidity that's stirred up, that we essentially shut off photosynthesis for short periods of time during storms. This also happened here. Same kind of thing. You see a lot of variability, which is reflecting the daily cycle of photosynthesis and respiration. You kick up enough turbidity, and this got up to something like 150 NTU units, which is, how would I describe this? Mayonnaise? Kind of, you can't see through it, okay?
So, excuse me, would Sandy just be off the left of the graph?
Sandy was, yes, just off to the left of the graph. We lost power during Hurricane Sandy at this site, so we had data for the first day of a windy day, and then it was shut off, and then we had to get out there, and because there was so much water, we couldn't get there for a few days. So we don't have Hurricane Sandy, sorry. We're trying. So turbidity changes things. I want to talk a little bit about this conductivity change. Conductivity changes a whole lot. Let me show you what this is discharge again. This is nitrate concentrations. Those storms change the nitrate pattern significantly. You're seeing there's a pattern here which is, I've not plotted in a way that you can see it, but there is a daily pattern in nitrate which follows consistently with the daily pattern of oxygen uptake. And from that, we might be able to get something which is a net photosynthesis, net respiration rate out of this. But what I want you to note is the dramatic change in the nitrate concentration and where it occurs for a second. And let me just go back here and show you the same pattern here for conductivity. Nitrate is the dominant anion in solution in these waters. Agricultural area, generally true in southern Delaware, all the streams we've looked at. So one of the nice things is that when we occasionally miss, our nitrate sensor goes down, that's usually because it runs out of a reagent. We can sometimes fill that back in by looking just at the conductivity, because the correlation is, it's like 0.98 correlation. Over short times, it switches. The correlation changes a little bit from time to time. But over short periods of time, we can do that. And this is true in all the streams. So we have at Salisbury State University, which is in Maryland, just south of Delaware, they've got people out there who are using just conductivity sensors to get estimates of nitrate loads. Correlation is just as good there as it is where we are. It's an agricultural situation. So the thing I want to point out here is every time there's a storm, nitrate goes down, phosphate goes up. Part of this is analytical because our phosphate sensor, we don't filter the samples, so we get a little bit of what would be absorbed phosphate on particles that gets included in our samples. We do correct for the turbidity associated with those particles. But this may be dissolved phosphorus, or it may be reactive phosphorus on the surfaces of particles that's coming out. But basically there's a spike in phosphorus that goes up, and the result of that is, when we look at this is now loads, so this is in grams per hour, it's concentration times flow. When we have a storm, the phosphorus loads go up by a factor of 20 often, sometimes up to 50. The nitrate loads go up by a factor of 2 to 5. So storms are really, really important in terms of transport of phosphorus downstream from watersheds in our settings to the marine and estuarine and marines receiving waters.
Do you know why that is? I mean, is phosphates banned in detergents in the state of Delaware?
Yeah, I think what's happening is that these are pretty muddy environments, and I think we really resuspend a few millimeters of sediment, and with that, the pore water where this is down in sediment, and I think that's the spike in turbidity has to be coming from somewhere. It's not coming from the. I have to explain Delaware drainage. We don't have surface streams. When it rains, the water soaks in and it soaks laterally. Yeah, it's like you. So I think what's happening is the flow gets fast enough. You start stirring up the bottom. You're releasing particles that have absorbed phosphate on them, which are now in water that's more dilute. So some of that's going to be desorbed. If it's not desorbed, it's going to be. We're going to suck the particles in, and we're going to analyze that anyway. And also, you have resuspension of pore waters in these systems due to the flow. Okay, let me talk about marsh studies for a little bit. The Murder-Kill estuary that I talked about earlier is a marsh-dominated estuary. The estuary, the actual water flow path is about 10% of the area of what is gravity, the water plus the wetlands, associated wetlands. This is the waterway here, and everything that you see here that's stippled is the marsh. And someone was asking me about the St. Jones River. That's the St. Jones River, which is the next river north. And the important part about this is that this estuary has a wastewater load, which is, it has the single large wastewater processing plant that does all of Kent County. So it covers all of the municipalities from Smyrna, Delaware to Dover, Delaware, and all the way down to Milford, all drain to this one little tiny estuary. So it actually has a nutrient load associated with wastewater, which is enormous when you consider the population of the watershed. But it's because it's piping in water from adjacent watersheds. And so we've been working on this estuary, and I'll talk about two different studies here in a second, but since 2007. When we did it in 2007, it was manual hourly sampling that we did there, manual dipping and recovering samples, and I'll talk about the new instrumentation we have here in a second. So the management questions was, to what extent can we treat the marshes? It's really, the question they asked is, are the marshes a source or a sink of nutrients? If they're a sink, can we include those in our management and say, we can put out this much because of nitrogen and phosphorus because we know that the marshes will remove more, and what gets out to Delaware Bay will therefore meet the targets that are set for Delaware Bay. That's really the question. And the other question, just in general, was how do the loads from the marshes, Kent County wastewater treatment plant, and the watershed compare? Which is the large source? I can't actually answer this yet because we don't really agree on how to properly estimate the nutrient loads from the marsh, because we only sampled 5 times for 40 hours. So we don't really have a good answer to that question yet. So one of the questions is, how do external forcing, winds, tides, and rainfall affect nutrient loads? To what extent, this is an interesting question, to what extent does the organic matter coming from the marsh affect the biological oxygen demand and therefore the oxygen concentrations in the Murderkill? The Murderkill is a really strange system. It's very turbid, there's very low net photosynthesis, and yet we have very low net production of new organic matter, and yet we have really low oxygen levels in this system. Because, in part because we're draining material from the marshes in the form of organic matter, which is reactive enough that it consumes the oxygen without photosynthesis to replace it. And the second thing is we actually drain waters from the marsh, which are themselves suboxic. So the poor waters that are draining out of the marsh into the Murderkill estuary already come in without any oxygen. And so when we're draining the marshes, we're not starting from saturation, we're starting from the level of oxygen that was in the water coming off the marshes, which is much reduced. So these are the scientific questions as well. Traditional methods of analysis were forced into this because of the idea that if we're really trying to quantify carbon sources, there's particulate carbon, so we had to do particles as well. There's no method that I know of that's going to give you particulate carbon, particulate nitrogen, particulate phosphorus. So we basically did everything manually. 5 sampling periods, each of them 40 hours, hourly sampling, up to 12 people working on the sampling team. Lots of people involved in this. It was exhausting. Lots of interesting data came from it, but I will never, ever do this again. So what I want to point out here, look mostly at the ammonium and the DON, I guess are probably the best ones to look at here. What we discovered is that most of the time the concentrations are fairly low, and they're low anytime that there is water coming into the marsh from the estuary. So the estuary is low in ammonia, low in dissolved organic nitrogen. But for a few hours, 4 hours during ebb tide, is when you get these spikes of things coming out of the watershed into the marsh. So it's limited to about 4 hours, sometimes 5, sometimes 3, about 4. And you have these peaks, they always occur, start towards the end of ebb tide. They end abruptly in all cases, so in 1 hour they switch from concentration, and that's actually the change of the tide that's causing that. And so this was a little bit hard to explain initially why it's all coming out in this little narrow thing, but I think we understand this a little bit better. Just to give you an idea what's happening here, let me stand on this side. Imagine you're at low tide, and so you're at the end of ebb tide, and the first water that comes into the marsh is going to have low salinity because it's going to be the least saline water that was in the estuary. So the water from the watershed mixing with the estuaries. All of that mixing is now moved downstream. The first water that comes in at low tide is going to be what I call Murderkill River water. So it's the lowest salinity water in the estuary, adjacent to where the input to the marsh is. And then so the water will then come in, and then the next water that comes in is going to be Delaware Bay water. It's going to come in from Delaware Bay, up the Murderkill, and into your marsh. So pretty quickly, we go in a couple of hours, we go down here to something that's dominated by Delaware estuary water. So now here we are at high tide. High tide, we start, the water starts flowing out. The water that flows out is pretty similar to the initial water that was in Delaware Bay. The water from Delaware Bay came in, didn't react with very much, turned around, went right back out. Until we get to towards the end of ebb tide, and then there's this spike of water that's coming out of Webb's Marsh. What we think is happening, and there's some work from Bob Gardner, did some interesting work on this in South Carolina, is that the first water, that fresher water that's coming in, it's actually going into the channel and flowing into the pore spaces adjacent to the channel. Those pore spaces are just the sedimentary pore spaces. They are yucca burrows, which is, we remember from South Carolina, so they're burrows of organisms, and they're old root channels associated with the Spartina that's living there. And water comes into the channel. The first water flows into the pore spaces. And then we have this water from Delaware Bay that comes in, and it just flows up the channel. It can't flow in the pore spaces. They were filled up earlier with the fresher water. And then all that water flows into the marsh, makes the marsh look beautiful when it's flooded, comes back out, and only at the very end you get this spike of water coming back out of the pore water into the channel and out of the marsh. And that's how we explain all of these spikes that occur towards the end of ebb tide, the last little bit of ebb tide is where we see these. So this observation, we wouldn't have been able to do this without some information that we gathered from the manual sampling, which allowed us to look at dissolved organic nitrogen, particulate organic nitrogen, and other phases and how they behave differently from these dissolved phases. So anyone has questions about this, I can talk about this a little bit more after the talk. So the last thing I want to talk about, and I'll do this pretty quickly, is the newest instrument we have. And I won't talk about the scientific issues, but let me just introduce the instrument. The instrument is called the LOBO. It's the Land Ocean Biogeochemical Observatory. It's an off-the-shelf commercial device that's built by Satlantic in Halifax. It has pieces that are built by Wet Labs, which is in Oregon, and Seabird, which is in Washington. And all of those three companies now, by the way, are all owned by the same company called Hawk Hydromet. And I have their brochures down here if you want to see what they do. This is an instrument that has connection to the surface, which is for communications and power. It has a data logger and data management system on board. It has a WQM, which is a CTD plus a turbidity sensor plus a chlorophyll sensor. It has this particular version has a separate CDOM system, but the newer versions now have that CDOM built into the WQM. It has something that I can only describe as a miraculous instrument, which is this SUNA nitrate sensor. And this is the Cycle P, which is a single in-the-box autoanalyzer, submersible autoanalyzer for doing phosphate analysis. And for our application, we put this on a dock that's owned by the state of Delaware. It's actually a bird watching dock for the Fish and Wildlife Department. It's Lindy here somewhere. This is what those guys do. They have a dock there where they go out and count birds, and they're letting us use their dock. And we've built onto this a little railroad track to lower this instrument up and down. And the wastewater treatment plant came out and said, that's too heavy for you, let's put a winch. And they dropped a winch in there for us, which now has power on it. Didn't have it at the time the picture was taken, so we can take care of all that. The power is from a solar panel here. All the data is transmitted via cell phone out daily, or actually hourly. And we basically service this instrument. Downside of this instrument, it's not a downside, it's a problem with any instrument. Fouling is a major issue where we are. The second thing that's a major issue is turbidity and basically clogging. So we have to go out there. In the summertime, we're out there about every week, every 10 days. In the winter, we go 3 to 4 weeks because we have fewer fouling issues. I've pretty much said all of this. This is just to show that we can calibrate this against manual methods. It's pretty good. The nitrate measures high, and everybody I've talked to has demonstrated the same thing, that the nitrate values in intermediate salinities tend to be a little bit on the high side. They're better at low salinities, and they're better at high salinities. We haven't figured out how we're going to handle this yet, but the sensor is pretty robust. I should say something about the SoMAS sensor. The SoMAS sensor, we put it in the water. It didn't work the first 3 days, and we had to go out and play with it. But it turned out that there was, SoMAS has a little brush, so before it does a measurement, it takes a little brush and here's the optical pathway, and it takes the brush and it goes shoop, 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 cleans the pathway, does its measurement, and we had not properly aligned the brush and it got stuck in there. And since those 3 days, it has worked continuously for over a year. We're just now celebrating a year of its operation. It's very robust. I'm very pleased with that instrument. Of all the instruments we have, that's the one I'm happiest with.
How much does this little beast cost?
Oh, it's trivial for a wastewater treatment plant. It's about $100,000. So a wastewater treatment plant, that's for the Kent County wastewater treatment plant, they have an equipment budget of about $3 million a year. When I asked them if they would buy this instrument from an instrument like this, there were some other instruments we looked at. It took them a week to place the order, and a few weeks, about 3 months before it was delivered. So for a wastewater treatment plant, this is not expensive. For scientists, this is expensive, but that's part of the reason you have to work with environmental managers. A couple of things. This is data from our LOBO. This is salinity data. This is nitrate data. Someone asked me about Hurricane Sandy. Hurricane Sandy, the feature of wind events. So Hurricane Sandy, let's initially talk about a wind event on this system. What happens during a wind event, if the winds are from the north or northwest, we have a downwelling favorable wind, water moves to the right, it comes into Delaware Bay. We essentially get a big plug of salt water that comes into the whole bay. And it comes all the way into our main tributary. And essentially, that salt plug stops any flow of fresh water downstream. So we essentially, this is the normal salinity that we would see on a normal day. During the storm, there's no fresh water coming downstream. Of course, it all comes down after the storm. The water doesn't disappear. But one of the things we've learned is that the impact of Hurricane Sandy on the murder kill didn't occur during Hurricane Sandy. It occurred the 7 days afterwards. So when you focus on just what's happening at Hurricane Sandy, you can understand the physics. If you want to study the chemistry, you have to give it a little bit more time. So Hurricane Sandy, this was a nor'easter here. It did the same thing. This was just a rainfall event which did not have winds. So we're starting to look at this system and what happens when it's windy, particularly offshore winds, what happens when it rains, what happens when both happens. And they have different effects on nutrient loads, nutrient concentrations, and ultimately nutrient loads. This is just to show people who are interested in mixing curves. We can, a few days of data from the LOBO, we can have 100 samples, and we can do mixing curves really well, which means we can estimate what the flow-weighted average freshwater concentration is coming in from measurements we make more or less at the saltwater end of the estuary. And so one of the things we're looking at is how this flow-weighted concentration changes over the seasons from these extrapolations. I'm not going to talk about this. Anybody wants to look at the data, go to look up LOBO on the web and type Bowers, Delaware, and you'll have all the data. All the data is available for people. You go to that site, you can actually plot it all. There's a plotting routine built in the back of this. This is a service provided by Satlantic. We pay for it, but it makes it really easy to get real-time data. The data, 25 minutes after every hour, there's new data downloaded. So a wastewater manager who is interested in regulating his waste discharge in order to maintain environmental quality actually has real-time data, or pretty close to real-time data that they can use for management. So this is just a quick summary. Where are we now? There are some really good sensors out there. The CDOM sensor is amazing. Turbidity sensors worked, except for the time that something grew right on the surface of the window. Turbidity sensors work. The chlorophyll sensors work really well. Some of the sensors we're having problems with. I don't know whether we'll ever get the phosphate sensor to work because our system is so turbid that even with filtration, there's enough stuff getting in to the autoanalyzer that it affects the ability for the little cyclophosphate analyzer to work. There are constantly improvements. There's actually, there have been a whole bunch of software improvements in the last year that we've updated. That's been very good. There's also hardware changes in how they manage the power and all sorts of other things that are happening. So there's lots of new things to come. But there's certain things I think they're never going to have sensors for. I'm not a pessimist. I just think there's some things that are going to be really difficult to measure in flowing water and under in situ conditions. And so there still will be a place for people who want to do water chemistry to keep us in business a little longer. I think the present sensors we have, just because of the frequency that we can do the measurements, we're seeing all sorts of things we never would have seen if we were sampling only every 2 weeks, which is kind of the high frequency we've done in the past. We can do hourly things. We actually, for some of these instruments, we can do sub-hourly measurements, but hourly seems to be working pretty well. The biggest thing that I'm having to deal with is learning how to deal with a dense data stream to interpret it. And fortunately, I have really smart graduate students who know how to do time series analysis, and postdocs and colleagues. And I'm apprenticing to them, and I'm hoping that I'll be able to do some magic that they can do with those kinds of analytical techniques. There are lots of new sensors coming online. I have a colleague who's working on electrochemical sensors. Bob's working on optodes. There's the company that's called SCAN that makes the other nitrate analyzer is developing all sorts of new optical sensors for wastewater applications. Some of those are likely to have applications in the environment as well. And it's a good thing that they have the wastewater business, because the wastewater business provides them with development money, so that the cost of these instruments are likely to come down as these are used. Things that we're thinking about now are new modes of operations for these automated sensors. Can we put them onto boats and kind of drive around with them? We're talking a little bit with a new faculty member about putting them onto AUVs or gliders. That's a possibility. I think this, for me, is a really big challenge. How do you look at this large data stream, get some useful information, not just the concentrations, but useful information to managers on real time? And that's something that Brian Swankowski and I are working on. How do you take the data and highlight those things that are going to be of interest to the watershed managers and get that information to them at that time? And if we get to that point, we're going to get to something which I call responsive management, where the watershed managers are not managing on terms of average annual or average seasonal concentrations and loads, but can actually look at the present, the right now concentrations and load, and make decisions that are better for the environment. And with that, I am done. Thank you.
Well, as you can see that, Bill, you still follow my directions. Of course, a 40-minute talk.
You didn't stick to your time.
I know, I'm just joking.
No.
But we have time for a question or two, and then we'll have to retire.
If anybody wants information about the Lobo, I brought their literature with me, so if anybody wants to take that, you can. I also brought fact sheets for the 2 sites that we're currently operating that are available, one for the Lobo site and one for the Delaware site, so you're welcome to have either of those.
I do need to correct something. You did say, you mentioned me as optical sensor here. You should talk to Ching about
Ching, sorry.
About that. Sorry, that's the big guy.
Okay, well, I apologize.
No problem. Okay, questions?
Yes.
So what are your top 3 measurements never to be made by a sensor?
That's a good question. I think the hardest part is going to be separating particles from dissolved and analyzing those separately. And I think right now we have no methods, automated methods that I know of, that are going to do the particles at all. You can, in principle, trap them on a filter, but we're not getting the analytical data until subsequent processing. So I'd say particles are the biggest problem, and separating particle versus dissolved for some sensors is the problem.
Back to the having the strange behavior of phosphate during fall.
Yeah.
Do you think that has to do with farmers or people fertilizing their lawns?
I think, yeah, the answer is probably not, because they're mostly fertilizing in the spring. We do have a winter wheat crop, but that would have been November or something that they're planting that. I think it's really just that the steady state gets tenuous as light is going away in the fall. And so that's a sensitive time for maintaining that steady state, and then one big event can shift that. I think during the summer, we tend to come right back to the same steady state. Looks like that. But it's not that it's, what was surprising to me is I thought from the data we'd sampled this Millsboro site before manually, and we had seen that there was a general trend towards this new state. What wasn't clear to us then is that a storm could switch it over very quickly.
So I think we're going to retire for lunch now, and the conversation can continue there. And there's also, as I mentioned in an email earlier this week, there's a period of time after lunch where students can meet as a group, if you wish, with Phil, who will be in the Okubo room for a period of time. And so I wanted to thank you again, Phil, for a really great talk.
Thank you.